Okay, part 2. And now I talked about how you get your components on the screen. In this half, I want to dig down into actually how those things get drawn and talk about the graphics context and dig into what's actually going on behind the scenes to get those pixels onto the screen or into an image. I'm going to start by having a look at the main class that you'll be using when drawing, which is the graphics context. If I can find it in here, graphics. Let's just have a look at the class. It's a non-virtual class. There are no virtual methods in here. The graphics class itself is basically a wrapper around other simpler rendering functionality. So it has a whole bunch of methods. Starting with like setting fill types, gradients, the opacity you're going to be drawing with, setting the color you're going to draw, setting the font you want to draw with, and then you can all these methods to draw some text, to fill rectangles, to draw rectangle outlines, to do rounded ones, checkerboards, all kinds of things. Ellipses here, lines, dashed lines, horizontal, vertical lines, stroking paths, arrows, for drawing images. So basically a whole bunch of handy functions, all of which are pretty straightforward, none of it's rocket science. What happens inside this class is that all of these calls, some of them go directly through to lower layers that actually do pixel pushing operations. Others are kind of high-level composite operations that may call some other stuff internally and then pass through to lower-level operations. You get a graphics class, a graphics object to work with. You generally don't ever create them. You'll get given one when your paint method's called, and you can create one if you want to draw it into an image. So you'll create an image, and then you'll create a graphics object, give it the image as a parameter, and that'll let you draw into the image. But that's really the only two times that the only two ways you get one of these. Here is that. I think most of you will have used one of these many times, so I'm not going to go into details about how to actually draw things. I was already using one earlier for the demos, but I will go into a bit of internal background on what's actually going on when you call this thing and say fill a rectangle or draw an image. So here we are in the JUCE graphics module. In the context section, we have this graphics context file is the graphics context that we all know and love. But the other files in here are ones that you probably never looked at. This one here is a base class, and this is a low-level graphics context. You're never going to need to create one of these, but I will show you what's going on because it's quite important in understanding what's going on behind the scenes. The graphics object that you're painting with has one of these inside it, and this is a virtual base class. And this is basically a cut-down graphics object. It does a few things: basic drawing of rectangles, drawing of images, clipping, and this is a virtual base class. There's I think 3 or more, maybe 4 subclasses of this which you actually use. If you're running on iOS, on iOS or OS X, then you're going to get a version of this which actually does all of these methods via core graphics. And these calls will go straight through to a core graphics call that might draw a rectangle or draw an image, and then we let the operating system worry about how that works. If you're on Windows, where historically, and certainly when I started doing all this stuff, there was no actual decent rendering engine that could do anti-aliased paths or fonts or anything, then I wrote my own. So we have a software, the low-level graphics software renderer, which is a bit of a mouthful, but this is an instance of that which actually draws using the CPU into an image. So this will work on any platform. And what you're going to get from all of these is a pixel by pixel, the same result. So if you use a core graphics context or one of these software renderers, or an OpenGL renderer, or whatever other crazy ones we come out with in future, the idea is that what you actually end up with will look exactly the same on the screen. So the software renderer...
is that strictly true at the moment?
That is strictly true at the moment, yes.
Including the fonts?
Okay, it's not strictly true at the moment. Mostly true. The fonts there's a slight difference in the fonts because on OS X, Core Graphics has some sort of funky font renderer which fattens the glyphs slightly using a cunning algorithm that I can't quite work out. My software renderer will be pixel for pixel, the same as the OpenGL renderer, I think, claim. Because they both use the same font rendering engine, but it's slightly different to Mac. On a high enough resolution display, you would never know the difference. But yeah, if you're still using an old VGA monitor and sitting very close to it, then you may go, oh, that I think that character there is a little blurry or whatever. But yeah, certainly if you're drawing paths or well, paths are actually 90% of what you draw, but paths, images, and fonts are the only three things going on. Paths will be the same, images will be the same. Yeah, fonts, no one will know. The software renderer, I will just quickly show you what's going on behind the scenes in that one. There is not that one. You can dig into this stuff at your leisure, but there's a big file here called rendering helpers. So if you're interested in digging around in the back in the basement of JUCE and seeing what's in there, this one's a good one to look at. Rendering helpers. This is a big old file. This is basically a 2D rendering engine that's been templated out, and this is code that's used in common between the software renderer and the OpenGL renderer. So this stuff it'll take a path and it'll flatten it, and it'll then draw like horizontal pixel-wide lines to render paths, and it'll do all the anti-aliasing at the edges. There's stuff in here to handle fonts and caching the glyphs of those fonts. And yeah, if you're ever bored on a long winter evening and you want to dig through some code, there's a lot in here to keep you entertained. And this is used internally by currently the two main renderers for Windows, which are GL and Software Renderer. The Core Graphics one is much simpler because most of the calls are just straight through to OS X. Now the way these contexts work is they're very stateful. So generally, at any moment, a graphics context will have a state which consists of a clipping rectangle, a color, possibly a fill type, because you might set the fill to be like an image fill or a gradient fill, and a transform. And as you push and pop, as you make changes to the graphics context, you'll often want to say, okay, save the state at this point, and then I'm going to change the color, change the transform, I'm going to draw some stuff, and then I want to go back to the original state I was in before. And this is generally how components get rendered. A parent component will be painting itself, and then it's time to paint its children. So it'll say, save the state, save the clipping rectangle, save the color, save position, and then it'll let the child do whatever it wants, mess up that context, and then it'll pop the state back to where it was before. And to do that, we have a function in graphics, which I've lost. Just get that file again. We can save state and restore state. And we also, because we all love RAII, don't we? And that's not optional. We have a scope to save state, so you can't forget to restore the state. So if you're drawing some, so let me show an example of this. If I go back to my my earlier main component and look at the code. Here's the bit where actually let's get rid of I'll just get rid of the other things in here for the moment, so we can see the painting. So there's our hello world. Let's say I want to draw half of my hello world in red and half of my hello world in green, but I don't want to do it by actually just drawing the fonts. I want to actually clip it like down the middle of a letter or something. So what I could do here is, for my graphics, I can save the state, and then I can clip it. I can, is it reduce clip rectangle, I can't remember the name. So first of all, let me see if this works. I'll just restore state again. So there we go. We've got hello whoop, because what I've done here is I've added a clip region. So before I draw the text, I'm clipping so that only half. This graphics context can now only draw into the left half of the component. So my hello whoop gets truncated. But before I did that, I hit save state, which made sure that everything, the entire state of that graphics context is now pushed onto a stack. And then when I call restore state here, it gets put back. So after this, I can then copy and paste this code, which you should never do. And I will say that I need to remove from right. And now I'm going to change the color and do the right half of this in red. And then we've got hello world with half green and half red. Because after I restored the state, it meant that I was back to my unclipped version I could draw anywhere, and I can clip it down again on the right. So this is kind of the same thing that's going on behind the scenes all the time when you have components. And because when you're drawing into a component, like we saw before with the painting is unclipped stuff, before your paint method gets called, the code behind the scenes will have made sure that it's been clipped into the right region. But after it's let your component paint itself, it needs to go back and let the other bits paint. So this is how you do it. And stuff like this actually maps on in a pretty one-to-one mapping on rendering engines like Core Graphics, where these calls will be pretty much going straight through. But in all cases, it's kind of expensive to save and restore the state. So in general, it's not something you want to do a lot, but that's how that works. We also have some transparency layer stuff. So this is kind of advanced graphics. What you can do, it's a bit complex to show an example of this, but if you're about to do a bunch of renderings to this graphics context where you then want to do something, then you want to change the opacity of the whole thing, you can begin a transparency layer, do your drawing, and then call end transparency layer. And then whatever opacity you gave it when you started is what will be applied to that whole thing. Now, that's a very different, I'll show an example to show how this is very different from simply drawing with lower transparency. So if we go back to our example, I'm just going to get rid of all this hello world stuff. I'm going to draw two rectangles. So I'm going to fill rect 10, 10, 100, 100. And I'm going to do that in, not in green, but in green with an alpha. So I'm going to do this half opaque. And I'm going to then draw another one in half opaque blue. And I'm going to make these overlap slightly. So I'm going to make this one at, say, 60, 60. So there are our two semi-transparent rectangles being drawn. Imagine we did the same thing now with the transparency layer stuff. So I'm just going to quickly copy and paste these because it's easier. So instead of drawing two 0.5 alpha rectangles that overlap each other, where we get the overlapping bit, let me draw two solid color rectangles, but draw them both into an alpha layer. So I'm going to say G, begin transparency layer, and let's make the whole thing 0.5. And then I'm going to take away these alphas on these ones. So these are now solid, but the whole thing is transparent. And then it's that's actually correct. I'll turn the alpha down on here, so we can actually see it more clearly. But the overlap is gone because the two things are solid. But the overall, the whole after the two things have been rendered solid, the overall thing is now rendered down with a 0.5 transparency. Now, this mechanism behind the scenes is how you can turn down the alpha on a whole component. Because when you have components and you want the whole thing to fade in and out, to animate things coming and going, you can't just draw everything in it with a different alpha, because you're going to get strange overlapping, blurring colors between the items in it. So you have to have some mechanism like this, and this behind the scenes is what would happen if I set the alpha of my component, which I can also show. If I go back to let's add the blob back. So there's my blob. I'll just get rid of this stuff here. So now I have my red blob. But say I want to fade that red blob out. Components actually do have a set alpha. So I can, as well as adding a transform there, I could take my blob and set the alpha of it to 0.2. And we should see a faded red blob. And behind the scenes, before the paint method on here gets called, then some code will call begin transparency layer. It'll let this thing render itself, call end transparency layer, and that's how that gets done. And that would be a very different result if the blob just rendered a 0.2 alpha red blob and a 0.2 alpha blue blob.
What actually happens in the software renderer when you do this? Does it render it to a separate bit of memory? Sorry.
Yeah, so I should say, if you're going to ask a question, wave at Chris over there and he'll bring you a microphone.
Cheers, Chris. So what actually happens in the software renderer during this? Does it render the rectangle to memory and then copy it all across, multiplying all the stuff and adding? Something
happens. It could be it could be rendering to memory. It could be rendering to a GL texture. It could be rendering to, I don't know. It doesn't matter. The point is, the result should be the same. In the software renderer, yes, it'll just create a quick off-screen bitmap. It'll render into that, and then it'll blit it down. So certainly, if this is an OpenGL renderer, it'll be a frame buffer. So yeah. If you do it in Core Graphics, we just tell Core Graphics to do that. I don't know what it does.
Yeah.
Probably, I think something quite inefficient, judging by some of the performance. But it'll depend entirely on what you're running on. So yeah. So yeah, actually, so behind the scenes it can be a pretty inefficient operation. It's like the software renderer will be slow because just moving that much memory around is generally a bad thing. And especially on a high DPI display, actually creating an off-screen bitmap, filling it with stuff, and then blitting all that, moving all that data back into memory and compositing it can be pretty painful. Yeah, question?
I have a question. I use this render to image quite a bit, so I create a graphics context on the fly with an image as a constructor.
Mm-hmm.
Is that heavy? Is creating the graphic context itself, is that a heavy operation? Or
creating the graphics context is not heavy, but basically free. Certainly not something you should worry about, but creating an image could be.
Yeah.
Especially if the image gets cleared, then that that could be a lot of memory. If you're doing it in OpenGL, it'll be very fast.
Yeah.
It entirely depends on the rendering engine. Okay, so let's look at some more rendering operations. Going back to my component here. Just put this somewhere we can see it. And get rid of my blob again. I'm going to quickly look at paths, because a path is kind of the most important shape drawing class that you need to know about. Behind the scenes, if you call your graphics and tell it to draw an ellipse or draw a line or pretty much anything that isn't a font or an image, behind the scenes it's probably going to create a path and fill the path, because most operations do translate down to filling a path. So the simple example of this, let's take a path and let's add an ellipse, and let's give it some coordinates. Paths, generally, you create them by creating one on the stack, and then you'll add some things to it. So you might start a subpath and then do some lines or do some quadratics, and then end the subpath, and then create it at a very low level by actually building lines. Or you may say add an ellipse, or add a rectangle, or add, I think there's a bunch of things like to add star shapes and various different geometric shapes. And then you will render it by setting a color or a fill pattern. I'll do fill patterns in a minute, actually. Let's make it red. And we'll fill the path. So you should see a path appearing there. So there's our path. And hands up, people who are familiar with how paths work in terms of the inside-outside winding rules and things. Anyone? Is that one there? Okay. Yeah, a few of you, but not many. When you have complex paths that cross over themselves, you're going to get bits of them that where they overlap, and we have rules for whether those bits get filled or not. It mainly matters when you're drawing fonts, because glyphs tend to overlap, and to actually have glyphs that are quite complex without holes in, you need to set winding rules. I'm not going to go into too much detail on that, but when you're actually generating paths by hand, you will find that you need to know that kind of thing. What I'm going to do here is illustrate it by adding another ellipse. So I'm going to take the same path I had before. I've added my ellipse, which is actually been generated internally by 4 cubic curves. So it's actually basically four sets of 3 points, are the contents of that path object. I'm going to add another one now, and I'm going to make this one a bit smaller. So this is going to be inside the other one. So you're not going to see any difference here, because 2 paths, you've got the outer one and the inner one. It all becomes one path, the whole thing gets filled. But when I change the winding rule, if I can remember the name of the function for that, I'm just going to have to look up. I think we went false for that. Then we suddenly get a path with a hole in. What this has done is that you have either a zero or non-zero winding rule associated with a path object, and that tells the renderer whether it's quite hard to describe, but whether when it has nested parts of the curve, whether ones that are inside others are also filled, or whether it should alternate the filling and not filling. It's something you might want to go and have a play with. It's kind of fun to use. If I add another one inside this again, that's even smaller, then it'll actually come back. So let's make one at 40, 40, 50, 50, and then we've got a circle within a circle. But this is actually still only one path. Each one of these is a separate subpath, but when they overlap, we've told it to always go in. And so as it's crossing each horizontal line of this path, rendering it, the rendering engine is going on, off, on, off. If I set my winding rule to true, then it'll be on, all the way across. It's pretty obscure, but it's quite a fundamental thing. If you actually get into geometry and path stuff, you will. Oops, that's not going to happen in that meeting. It's an important thing to understand. Next thing you're going to want to do with the path is to draw an outline around it. So we do that with a stroke type. And the graphics context actually has helper methods for this. So I can say stroke path, P, and give it a path stroke type. Let's say something we can see. So this is actually, it looks the same as before, but this is actually now an outline that's being drawn around the path that I just created. So I created my ellipse, it's drawn the path. What I'm now going to do is I'm going to change this so it's not an ellipse, because an ellipse is a closed shape. I'm going to do an open shape, So we can see that it's actually a line. So I'm going to say start a new subpath at 1010, and I'm going to draw a line to 100 something. Thank you, Clang. I did mean start a new subpath. So now this is a line. If you were to just fill that path, you get nothing at all. So if I do fill path, we'll see nothing. Because it's just a line, it doesn't close itself, and there's nothing to actually fill. But if we stroke it, then we do get a stroke. And the path stroke type class down there takes other parameters, so you can tell it what kind of ends, whether you want rounded ends and what kind of corner joint styles you have. So whether you want sharp corners or rounded corners, and you've got quite a lot of control over that. We also have some dashed path utilities, so you can have create a little array of dashed lengths. So you can say dash for 10 pixels, then leave a gap of 5, and then you can have arbitrarily long sequences, and then you can take a path and to dash. So what happens when you actually draw these things? It's I like to spend a few minutes just giving you an idea of how hard it is to draw these things, because it's kind of important when you're doing this stuff and trying to optimize your UIs. It's good, and I actually would recommend taking an app and actually just pressing step into. Go into a paint routine and just press step into a lot. Just go in with your debugger, just see how far down the rabbit hole these things go, and you'll start to get quite a good feel for how much work's involved. If you were to call the stroke path function here, it's actually going to create another path, which is the outline. So it's going to iterate all over the curves of your path. It's going to break it all down into lines. It's going to then create some extra lines that go alongside those lines in parallel. It's going to join those all into new paths. It's going to create a new path object. It's going to return that. It's going to then pass that onto the graphics renderer. Graphics renderer is then going to take that path. It's going to iterate all the curves. It's going to take all those curves and break them down into little line segments. It's going to put those all into a big array. It's going to sort them all. And then it's going to go along for each horizontal scan line, each horizontal pixel. It's going to go through that path, and it's going to look for all the bits of line that cross that horizontal pixel. And then it's going to build a little table of 1 pixel high blocks, and it's going to draw them. Now, if you're using the software renderer, you can dig and you step into this, and you'll be there for weeks going down and down into all building these tables, sorting them, building the edge tables, and then doing the pixels all the way along here and compositing each of these pixels. If you watch what the GL renderer does, it does the same. But once it gets down to the horizontal pixel block step, it passes those as rectangles off to the GPU, and that all gets rendered. Which actually makes the GL renderer the best way we have currently for drawing paths, because it pretty much works in parallel. That the CPU is flattening these paths into lines and throwing rectangles at the GPU, which is then rendering them as fast as it can. So if you run something like our JUCE demo, which has our rendering demo in it. On this page we have some timing. So this is drawing some paths, and it's actually drawing filled with a gradient. And this will be using the core graphics renderer at the moment. So it's taking 3 milliseconds to draw that fairly simple path. If I turn on the software renderer, oh, that's actually better, which is surprising. But this is on a low-res display. If this was on my Retina display, it would probably be the other way around, because we've got a lot of pixels. And the software renderer is really efficient on rendering small things because there's no overhead of talking to a GPU. It just sets a few pixels in memory and you're done. But when you have big high pixel density displays, the numbers just get really crazy and the software renderer is never going to be very good. The GL renderer is kicking ass here. It's down to 0.5 milliseconds. And it's basically using exactly the same path as the software renderer, except when it hits the compositing stage. And at the compositing stage, all of the gradients, the colors within these gradients are being rendered by GPU shaders, and all of the horizontal pixel lines are being just thrown at the GPU for rendering.
So the paths are all converted to rectangles and then sent to the GPU, right?
The question is, are the paths are all converted to rectangles? Yeah,
but the GPU could do
very small
those.
rectangles. Yeah.
Yeah, but the GPU could do those. It doesn't have to have rectangles.
The GPU.
But you don't have the
The GPU can do it if you have, if you're using something like CUDA or OpenCL. What the GPU can't do, or at least I've never managed to figure out a way of doing with a normal GL shader, is taking a curve and rasterizing it, and then turning that into scan lines, because it has to. Okay, another approach you can take with GL would be to triangulate it. If you triangulate it, which was how I originally did this, it's fine, it'll work, but you'll get very poor anti-aliasing.
Yeah, that's the problem.
And what I wanted with the JUCE 2D renderer was to make something that was actually pixel for pixel the same as the software and the core graphics renderer. And for that, the only way I could find to do it until the next generation graphics APIs come along pretty soon is to actually do the anti-aliasing manually by the CPU. So even though you can't see on here, like the actual anti-aliasing around the edges of these are actually done as 1 pixel rectangles, and then larger pixels for the solid bits. And that's how the software renderer's always done it, and it works pretty well on the GL renderer. I mean, the performance is very good. It could be even better if we have, with the next generation APIs like Vulkan and Metal, I'm hoping we're going to be able to write something where you just throw the whole Bezier curve path at the GPU and let it do it in parallel.
Yeah,
and
that will be platform specific. Right?
No, that would be fairly cross-platform. But kind of like, I mean, you can almost do this with GL shaders, but not quite. I'm actually quite looking forward to that, playing around with that this year. That's on our roadmap.
Last question: do you have an idea why this core graphics is being outperformed by your software graphics renderer at the moment? Is it because of all the system calls? Or?
You know, if I put it on the other display, it might be different. I don't know what's going on in there.
No, that's what I always noticed between our Windows and Mac version. The Windows version rendering is really quick. Mac isn't.
It'll also depend what you throw at it. I mean, the core graphics stuff is very, very good. It's just in certain cases you're going to find one method's favoured, and like right. for example with the solid, if I do solid color, it might be different. Yeah, solid color we got GL renderer 0.3, core graphics renderer 0.8, software renderer 0.5. They're all pretty close. You will get differences when you render images, because okay, we've got software renderer will always be terrible at rendering images because just moving all that data back and forwards is going to be very difficult, and CPUs are really bad at the subsampling you need to do to filter the images as you rotate them. So we're getting actually. In this case,
it's always quicker.
Embarrassingly, it is doing very well. The core
Mm.
graphics is similar. The core graphics behind the scenes for that image is probably doing it in memory because it's not. If you use a core animation layer, it would be better, but we don't. The OpenGL will wipe the floor with all of them in this case because what's happening here is the image. In the JUCE image class, there's a flag to say whether the image has been changed. If you draw an image to the GL context, it has to upload the data. So it'll upload it to a GL texture and we'll use that to render it. But then it keeps track of that texture so that if it knows next time you draw the same image, if it knows it hasn't changed, and if it's still got that texture on the GPU, it'll just reuse it. So actually, this thing is cheating because every time it draws this, the data is already on the GPU and there's absolutely nothing, no traffic going backwards and forwards. So all it has to do is draw with the existing texture. And on GL, to actually draw an image and subsample it is that's just what they do. The chip is designed for that, so you're going to get blistering performance out of that. It's even faster with the RGB tiling here, which is practically 0. The reason drawing a single image is slower than drawing a tiled image is because when we draw a single image, we want anti-aliased edges. and because we're doing an affine transform on this. If you're just drawing an image as a fixed size and there's no need for anti-aliasing around the edges, then we can optimize. But in this case, this is actually drawing it as horizontal lines, like a path. It's basically taking a path, a rectangular path, affine transforming that, and filling it with this as filling it with that almost like an image texture. So this is actually, although it's going very fast, it's actually a pretty slow operation behind the scenes. Some rectangles are very simple to do. So software 1.2, Core Graphics 3. Core Graphics is normally better, sorry. Okay. So we've already started talking about images, so I think maybe carry on with that. We've got to finish in 10 minutes, so I want to get through a few things. Images, like I say, you can have different modes of using them. They can be in memory, which is great for the software renderer. They could be in GL memory if you're using a GL renderer, and you can explicitly create an OpenGL image using OpenGL image type. So if you want to forcibly get a frame buffer and draw into it, you can do that. And if you get an OpenGL frame buffer image and create a graphics to draw into it, that will use GL to draw into the image. Other stuff I should cover in the remaining time. We've got some glyphs being drawn here. In this, let me see the performances on here. This is a case where you're going to get the most, like we said before, the most difference between the different rendering engines. So the core graphics stuff will probably look better because they have some very clever algorithm I can't quite figure out. Our software and GL renderers, we now render fonts after years of me being hassled on the forums about JUCE's blurry font rendering. It's not blurry, it's simply correct. But okay, I get it. Some font sizes, it's a bit blurry at the bottom. So what we did, I think maybe a year or two ago, is came up with a new rendering algorithm where we snapped the fonts vertically, so that by looking at the height of upper and lowercase letters, so we'll look at like an uppercase H and N and M, things with flat tops. And we'll look at like the lowercase n's and m's and look at where the horizontal midline is. And then we snap all very slightly by under a pixel. We'll fit the fonts to the on-screen pixels. So the top and bottom lines and hopefully the bars in the middle of like a capital E will all snap nicely onto solid pixels. And then horizontally we keep everything sub-pixel so that when you see whole words and whole sentences, it doesn't look all wonky like you get on old-fashioned Windows, which I've always hated. So that's how we render it in the software and GL engines. For Core Graphics already does a wonderful job and does seem to do something fairly similar, as well as they seem to for small font sizes, they seem to pad out the thicknesses of the characters as well somehow. In terms of drawing fonts, text, we've got several levels you can go at. So you can either get your graphics objects and say, draw some text, put it here in this font, which is fine. Or you can create a glyph arrangement object, which is a glyph arrangement is a set of font glyphs all laid out in a particular layout. So that could be a page of text. You could have a glyph arrangement which is a whole page of text, and then you can reuse that glyph arrangement. So just draw this glyph arrangement, move it around, and if you're redrawing the same thing many times, that can be more efficient. Behind the scenes, if you just draw some text, it will secretly create a glyph arrangement and draw it for you. But you can manually create one and move it and keep it around. We also have a text layout class, which is an even higher level where you say, here's some attributed strings where you give it, say, here's a string of text with some colors and fonts, and you can build up strings of different types of fonts and text, and then say, lay it out with this width, and that object is a text layout, and then you can reuse those as well. And those are used internally for things like the text editor and other text editing classes. And SVG is another good one here. We have a full SVG parser and a whole set of classes behind the scenes to manipulate them. So if you want to load some SVG, the class to use is the drawable class. I haven't really got time to dig into drawables. I hoped I would, but a drawable is a special type of component. There are only a few types of drawable. We have a drawable path, we have a drawable image, we have a drawable composite, which is a set of other drawables. And these things, when you parse some SVG, you throw an SVG file at the parser, it will give you back a drawable. That drawable is a component, you can just add it to the screen. So that's what's going on in this demo here, is it's just throwing a component in here and moving the components around with an affine transform. But all the sub-parts being drawn, so all of the coloured subsections of these images, are a nest of other drawable components inside each other. Unlike normal components, these are a bit different because they own the child components. If you write a normal component, you're responsible for deleting your child components. But if you have a drawable, everything within it is owned. So you can treat a drawable almost like a by value type. You can pass them around, you can copy them, you can delete them, and it's just like a thing, kind of like an image, but it's shapes. This means you can parse some SVG and then do things to it, because you've got the whole SVG graph there as a drawable. So you could iterate through this graph and change colors, change positions of things within it, delete things, add these things together, and do all kinds of high-level manipulations on them. Something that came up recently in the forum is some people have been trying to inherit from drawables, which is not how they're intended to be used. Other components you inherit, you override things, you do add custom behavior. The drawable classes are meant to be used just as is. You don't inherit, you composite them, you put them together, you use them to build shapes like this, and then you draw that shape. And there's a bunch of places we use these around the code base. So you can have a drawable image, drawable button, where you give it a drawable to use, and that's instead of an image. So you can have a complex SVG shape, and that's your button very easily. And we use it for a bunch of other things. Quite a handy trick in the introducer or producer is we actually have a little SVG path converter here, which is, because we've got lots of SVG parsers in there, this lets you easily take an SVG path and turn it into a bunch of code which generates a normal JUCE path. So you can paste in stuff from an SVG file from the internet and turn it into a path, and then do whatever kind of JUCE rendering tricks you need to get that path onto the screen. Okay, I think because it's getting so noisy and so near, we've got 5 minutes left. I better stop and open up for questions before we go any further. Point at Chris if you need the mic.
Sorry, Jules, could you
Yep.
let people identify themselves?
Yes.
When I ask questions.
Give a brief introduction if you're.
All right, yeah. Well, we make VJ software called Resolute, and we use JUCE quite heavily for years and years. I think since 2000, I guess, so a long time already. So my question is that we have a lot of sliders, and how can is there a way to optimize it? Because it uses paths everywhere for draw linear slider, draw whatever. Is there, because you said paths, if you step into it, it's quite heavy. Would there be a way to, I don't know,
to optimize paths?
pre-render paths or whatever? Because if the slide is always the same size.
You can't re-render paths and pre-render paths, and actually, I wouldn't recommend trying, because actually drawing a path is probably faster than drawing an image of a path on almost all platforms, other than on GL where you're statically generating an image and then rendering it many times, which will be faster but much more memory hungry. The one thing I really should say, because this was a performance, talk about performance and graphics efficiency, I've gone all this way without mentioning profile it. If you've got a performance problem, first thing you do is profile.
Yeah,
So,
no, but you mentioned the path. The step into it's quite a bit of work, and you're just talking about the paths and how
yes.
much work it is.
Yeah, exactly.
So I imagine it's going to be heavier than
paths,
fill
okay,
rec.
yes,
right?
paths are a lot of work, but drawing an image is, although it's simpler, it's actually generally much harder for the processor because you're going to have caching problems. You just moving all that memory about is going to immediately be a big deal for the CPU. This never used to be true in the past. Like years ago when we had lower resolution displays, everything's fine because it's a small manageable amount of memory. But now you get high DPI displays and these things are just off the charts amounts of memory. Hundreds of megabytes.
So using the sort of set buffer to image thing wouldn't be...
set buffer to image is a component method that...
Yeah, which does its drawing to an image.
That may or may not be faster depending on the size of the component and how often it's drawn, and it's one of these things like performance these days. There are no easy answers. You've got to profile it and A/B it. Certainly, it's always worth trying the set buffer to image stuff. And there's actually another level you can go to with buffering to images. I didn't have time to get onto this in the but this is a component trick, high-level pro tip, which is components you can say buffer themselves to an image. If you're really advanced, you can create your own buffering to image methods that you can attach to a component. So you can say, you can actually add a little class in between the component rendering itself and being repainted, such that if you want to buffer to a special kind of image or you've got some sort of weird, crazy algorithm, you can actually intercept the paint and the repaint calls for a particular component and do whatever you need to do. This is actually how all of the OpenGL 2D rendering's done, by attaching these special rendering interceptors to components. And it actually renders it with OpenGL rather than rendering it in the normal pipeline. So I mean, we could talk for an hour about that, but that whether it would be useful for you depends entirely on what you're doing. But certainly we've done a lot of performance optimization in Traction, which is obviously people always full screen it. You've got all these complicated nested things flying around. So we've spent a lot of time staring at profilers, and you can often find some interesting low-hanging fruit in there.
Yeah. That will be interesting as a blog post. Well, we did this what we had, and that's what we did we profiled. We saw this happening. That would be interesting for us to say. Well, if you have a project that is a bit like what we did, these are the things you can think about.
Yeah,
that would be nice.
To be honest, the biggest gain we had with Traction was when we went to painting as unclipped, when we turned all the clipping off, so that these things were basically getting rendered, bang, just all these nested clips just being rendered with without the overhead of saving loading the graphics state. Right. That seems to be the big bottleneck for us, surprisingly. And the paths generally are pretty cheap, even though it's very, very complicated. It tends to be pretty cheap. And certainly if they're big, a big path will be much faster than a big image. Small path, small image, the lines get blurred.
Okay, thanks.
Any other questions? Okay. No, one at the back.
So it's also about rendering GUI performance. We just have the exact opposite of UI with lots of images to render, one for each knob. And currently we are trying to optimize this to display on high DPI and stuff like that. We are using set buffer to image. We haven't tried the GL renderer, so you think it might be...
If you're dealing with images, the GL renderer will almost certainly be faster. Because even if you're changing the image every time you draw it, which you probably aren't, the time to push it to the GPU memory as a texture and then draw it seems to be better than just blitzing it around with CPU. So definitely, I mean, it's very easy to swap the renderers out. You can change that, and in the same way in the JUCE demo, you can flip between them. Just try them out and see what the numbers look like.
Okay, thank you.
Definitely worth trying that.